Hi everyone. It's been a while since we spoke about instrumentation amplifiers. As I was just going through those lectures, I realized I missed two crucial points uh, concerning instrumentation amplifiers. Especially, this is very useful for circuit designers and embedded system designers who are going to use these instrumentation amplifiers in their applications. So I thought I'll spend this lecture talking about those 2 points. So to quickly refresh your memory, an instrumentation amplifier is a differential input, single-ended output amplifier. Um, the, the, the implementation amplifier structure can be seen as a cascade of a differential input, differential output amplifier, followed by a differential input, single-ended output amplifier. The second stage is like a subtractor with a finite gain. The first stage gain is given by 1 plus 2 RF by R, which can be easily found by drawing a differential half circuit. It consists of two non-inverting amplifiers. Okay, you can easily find that out. And the second stage gain is given by R4 by R3. So this is the differential gain. This is the differential to single-ended gain. Single-ended gain of R4 by R3. So the overall gain G is given by the product of these two numbers. So now the output signal of your instrumentation amplifier can be expressed as V0 equals G times V2 minus V1, where V2 minus V1 is the differential input applied to this instrumentation amplifier. Now if you notice one thing, we did not talk about what is the DC voltage level at the output of your instrumentation amplifier. Okay, we said that we just found out the value of V0 in terms of the input voltages. Now, since we are talking about amplifying differential signals, if the input is now, if the input happens to be a differential voltage signal with some common mode VCM, then assume that there is only a DC common mode. I'm not applying any differential input signal right now. It's only a DC signal of value VCM for both the inputs. Then if I do a quick analysis of the circuit, the voltage across this resistor, this node will come to VCM because it's an inverting amplifier and non-inverting amplifier in negative feedback. So V plus will be equal to V minus. So this node will come to VCM. The current flowing through the resistor will be 0. The current flowing through both the resistors, RF and RF, will also be 0. So what will happen? The node voltage across the resistor will be VCM, and this node voltage will also be VCM. So the output of the first stage, the differential output of the first stage, the DC voltage will be equal to the input DC of the signals. If VCM is the input common mode and the DC inputs of the signals, the output of the differential amplifier, the first stage differential amplifier, will also have a DC level of VCM. But since you are feeding it to a subtractor, at the output signal, the DC value will be 0. Right, because it's the output V0 is simply equal to, if let's call this node voltage as VO1 and this node voltage as VO2, your output voltage is simply given by R4 by R3 times VO2 minus VO1. Okay, we are aware of this. So which means even if this VO2 had some DC common mode voltage and VO1 had DC common mode voltage, it will simply get cancelled out. The output signal has no DC level here. Now this can be a problem in some applications. Let's say, for example, you are driving your instrumentation amplifier to an ADC. And it turns out your ADC this instrumentation amplifier happens to be a dual supply, running on a dual supply op amps, which means the output signal can go positive and negative. Let's assume it goes to a positive or negative value of minus Vp and a maximum value of plus Vp. So your differential amplifier, your instrumentation amplifier, produces an output which can go both positive and negative. But if you want to drive this, if you want to feed this output to an ADC's input, you need to know what are the voltage signals that the ADCs can operate on. Now if the ADC happens to be unipolar ADC, meaning it has only a positive supply and the negative supply is just ground. So your ADC may be operating on minimum input voltage of 0 and some maximum positive output voltage. In that case, I can't directly feed this signal. Okay, because your input, the voltage levels are negative here, I can't directly feed it. In that case, I may have to add a constant DC level such that the sinusoid now swings from 0 to 2 V peak volts. Okay, so that it is always positive. And that is by adding a fixed DC voltage to the output of your instrumentation amplifier. I may have to do that. If I have to feed it to an ADC, then I may have to do this. Now, how do I do that? How do I accomplish that? That can be accomplished by adding a block called as level shifter. Okay, a voltage level shifter, a DC level shifter. I can add a block called DC level shifter and shift its level. Now, there are some very simple circuit implementations for level shifters. How do you can use an op amp itself. So this is your instrumentation amplifier. I can just use an op amp to do this level shifting operation. So if you look at this circuit, what have I done here? I have used a simple inverting amplifier with an additional current source present here. You can apply the principle of superposition and find out the output voltage due to this differential amplifier or the instrumentation amplifier and the output voltage due to the common mode current ICM. So first we'll assume ICM is 0. If ICM is 0, this stage acts like a differential amplifier, a single-ended inverting amplifier with a gain of -1. So the voltage at this point is what? G times V2 minus V1 multiplied by -1. The voltage at this point will be G times V1 minus V2. So you are measuring the differential input voltages here, but with a negative, there is a 180-degree phase shift, which is fine, which may be fine in many applications. Okay. Now, if you want to find the impact of the current source ICM, you have to assume V1 and V2 are 0. So therefore, this node voltage will be 0. If this node voltage is 0, the current ICM here will flow entirely through the feedback resistor R. Right? It's an inverting amplifier, so it's a negative feedback. This resistor will carry no current. The one end of the resistor will be at 0 volts. The other end will also be at 0 volts. So the total current through the resistor will be 0. So all this current ICM will flow through this resistor and it will create a voltage drop of ICM times R across the resistor, and the output voltage will also be the same. So the final voltage can be written as this: G times V1 minus V2. This is your instrumentation amplifier's voltage plus ICM times R. So now I can choose my current ICM and the resistance value R in such a way to adjust my DC common mode value, the DC level at the output of your instrumentation amplifier. This is one way. There are other ways as well. This is not the only way to do it. I can use the same inverting amplifier and apply a DC voltage of value Vref through a potential divider R and R. Again, you can apply the principle of superposition. Assume V1 is 0 and V2 is 0. Then this node voltage comes to 0. Now if you observe this part of the amplifier will behave like a non-inverting amplifier for this input, right? So first you need to find what is the input appearing at the non-inverting terminal. That will be Vref by 2. That gets amplified by a factor of 1 plus R2 by R1, which is 2. So you will get Vref at the output. So the overall op amp's output, the overall output of this circuit will be G times V1 minus V2. That is because the instrumentation amplifier will amplify it and produce G times V2 minus V1, which gets multiplied by -1. So I have written it as G times V1 minus V2 plus Vref. Again, I can choose my Vref. I mean that is the choice of Vref is in the hands of the designer. You can choose it so that the desired DC level is attained for your circuit applications. But now this is messy, right? You have to add an additional op amp based circuit to just add this DC level. Can we do something to this circuit itself such that I get this operation? I'm able to amplify the difference, not only amplify the differential signal, but also add some DC offset or a DC output value, DC value to the output. Okay, a DC level to the output. Now how that can be very easily done by connecting a voltage source of value Vref to the resistor R4. So previously, if you look, the resistor R4 was connected to ground, right? This node was connected to ground. Now if I connect, instead of connecting it to ground, if I connect it to Vref, we'll see what happens now. So to find the impact of Vref at the output node voltage, I'm going to first assume V1 and V2 are short circuited. If V1 and V2 are short circuited, what will happen? The first stage outputs will also come to 0 and 0. If the first stage outputs come to 0 and 0, then the circuit is very simple to analyze. All I need to do is find out what is this node voltage V plus, and then this part of the circuit will act like a non-inverting amplifier. Okay, so all I need to do is find out V plus. Once I know V plus, the gain from V plus to the output, your output voltage is given by V plus times 1 plus R4 by R3. Right? See, this node is at ground, so I can treat this part like a non-inverting amplifier, op-amp based non-inverting amplifier, whose gain is 1 plus R4 by R3. So now what is V plus? V plus is simply a potential divider for Vref. Okay, V plus is a potential divider. So V plus is simply R3 upon R3 plus R4 times Vref. That's V plus. That will be your overall output voltage. Now this term and this term will get cancelled out. R3 by R3 plus R4. This is nothing but R4 plus R3 by R3. Both will get cancelled out and your output voltage will simply be equal to Vref. And that shouldn't surprise you, because if you see, right, V plus is simply beta times Vref. See, the feedback network of this part, right, this amplifier's feedback network is what? R3 by R3 plus R4. That's the feedback factor for the second stage for this upper amplifier. And once you put your amplifier in negative feedback, the DC gain for this non-inverting amplifier will be 1 by beta. So 1 by beta is your DC gain, and you are ensuring that the transfer function seen from Vref to V plus is equal to beta. So beta multiplied by 1 by beta, you are going to get a gain of 1. So from Vref to V0, the gain is just 1. So once you add Vref to this node, you can apply principle of superposition and easily see that the output voltage is simply given by G times V2 minus V1 plus Vref. So now I have added a DC level to my output signal, the instrumentation amplifier's output, by just making a very small change. I just have to make, instead of connecting this R4's node voltage to ground, I can now connect it to a voltage source Vref. So which is what is normally done. And if you look at your, so this, I have taken this from an TI instrumentation amplifier. This is an 8-pin chip, and you can see it has a reference pin. The purpose of this reference, the pin number 6 is a reference pin. This is an instrumentation amplifier. And if you notice here, this resistance RG is not programmable. It is actually fixed. So some chips come with programmable gain as well for the instrumentation amplifier. Some chips come with fixed gain for the instrumentation amplifier. Even in those chips where RG is external, you can still have the reference pin. Okay, I can set my output DC voltage using this reference pin. That's what this pin is for, and it's very useful. If you are going to feed your output, your instrumentation amplifier output, which can be a bipolar output, you may have to convert it to a unipolar output by adding some DC levels. Okay, so one thing to keep in mind when you are, let's say, building a circuit using this instrumentation amplifier, you can't, I mean, if you are going to drive it with a voltage source, you need to ensure that Vref is a good voltage source. What do I mean by a good voltage source? It should be a voltage source with very low source impedance. I mean, I can't just, for example, if let's say I have a supply voltage of VCC, I can't simply put a resistive divider and choose these resistance values, say Rx and Ry, in such a way so that I get the desired output voltage Vref, and then I can't directly feed this output voltage to Vref. That's not advisable. Why is that? Because if you see, the impedance at this node is resistive, right? It's going to two resistors. It's going to resistance R. I'll use this terminology here. So we were calling these resistors as R3 and R4. Okay, so here if you see this figure, I'm calling this R4 and R3. Let's not worry about the values here, 120K and 6K. Let's ignore that. We are going to call them as R4 and R3. So you will be driving a resistive load. The moment you are driving a resistive load, then this node voltage is prone to variations depending on this load. Okay, so one advice, commonly used advice, is to ensure that the node voltage Vref is of low source impedance. How do you accomplish that? You can just put a voltage buffer. Generate Vref first using resistive divider, and then you can connect a voltage buffer or another op amp like this and generate your Vref signal. This is again a very commonly used design application where they put an op amp in feedback configuration and feed this Vref to this output. If you have, for instance, is this the only way? Not necessarily. If, for example, let's say you have a Zener diode available to you, and it turns out the reference voltage that you are looking for, and it turns out you are able to find a Zener diode whose Zener breakdown voltage is very close to your reference voltage, then you might as well use a configuration like this. You might have a resistor and a Zener diode and generate this Vref. Okay, sorry, this will be plus VCC, and generate this Vref, assuming that the Zener voltage is Vref itself. Zener diodes are generally known to have low source impedances, so they will act like good voltage sources in the breakdown region, so you can then connect it as well. Okay, so that's something to keep in mind. The reference input has to be of low impedance, so therefore either you put a op amp or use some architecture which offers you very low output impedance. Now if you observe this instrumentation amplifier chip, we have so far accounted for how many pins? There are 2 input signals, so you need 2 pins are going to go for that. 1 output signal, so 3 pins have gone there. Then you will need supply pins, supply and ground pins, or for bipolar supply you will have positive or negative supplies. So then that will take up 2 more pins. So that covers how many? 1, 2, 3, 4, 4 and 5 pins. Now we included reference pins, 6 pins. So totally all the 6 pins are now covered. There are 2 more pins which are called filtering pins. Okay, FL, it's written as filter, FL. So those are called what we call as the filtering pins. So I'll talk about them in some detail now because it's very useful for designers to keep in mind. So what happens is that let's say you have some unwanted components in your input differential signal. If you have some unwanted components in your input differential signal, you may want to filter them out. Okay, you may want to remove them. How can you do that? You can take your instrumentation amplifier and simply put a low pass filter after that. Put a low pass filter after that and then eliminate noise from that. But anytime you add a low pass filter, right, you are going to add noise from the low pass filter too. Low pass filter will add an additional noise that can again impact your performance and noise performance. And it's of course additional components, right? You want to minimize the number of components. So you don't want to add a separate low pass filter or any kind of filter. Let's say it turns out that you want to reject a narrow range of frequencies. You may want to add a band reject filter. Or you may want to pass only a narrow range of frequencies. You want a band pass filter in that case. Can we do that in a much simpler way? And luckily, fortunately, the answer to that question is yes. Now, how do you do that? Is that you take this resistance R3. Initially, it was a single resistance R3. That's the input to your second stage. Okay. And split it as 2 resistors, R3 by 2 and R3 by 2. Now, you will have access to 2 nodes here. If you connect a capacitor between these 2 nodes, we'll see what happens to the circuit. If you connect a capacitor between these 2 nodes, if you look at this part of the circuit, right, it's a differential circuit. It is still a proper differential circuit with a differential input and differential output. Therefore, I can draw a differential half circuit for that. So I've shown in the first stage here. I'm calling this now VO1 and VO2. If you draw a differential half circuit, this capacitor can be drawn as C by 2 and 2C and 2C with the center node being at ground. Now if I ask you to find out what is the overall differential gain of this stage, which is the differential output divided by the differential input, that will be, you can easily draw a half circuit and find the gain. You can draw, I have not shown a half circuit here, but you can easily draw the half circuit. So the first, the inverting amplifier, the non-inverting amplifier can be reduced to something like this, RF and R by 2, followed by a low pass filter of value R3 by 2 and 2C. So if you find the gain of this different half circuit, that will be the gain of the overall differential circuit as well. So that you can easily find the gain of this non-inverting amplifier is 1 plus 2 RF by R multiplied by this low pass transfer function, which is 1 by 1 plus S R3C. So now if you see, by just adding one single capacitor without adding any additional components, see, capacitors are noiseless by nature, so that you are not adding any extra noise to the circuit. By just adding a single capacitor between these two pins, I was able to achieve a low pass filtering action. Okay, I was able to achieve a low pass filtering action, and the low pass filtering frequency is given by 1 by R3C in this example. So that's the beauty of this approach. So if I just take this resistor R3 in the second stage and split it as two resistors, I can then now give these two pins, make these two pins as external, and give freedom to the designer to add whatever frequency selective network they want. If you want low pass filter, you can just put a capacitor here and you get low pass filtering between these two pins. If you want, for example, band reject filter, then you can add L and C in series. Okay, L and C in series. You can draw a differential half circuit. It will reduce to something like this. You will have R3 by 2 and you can show that it will be this will be L by 2 and 2C. This is what the circuit will reduce to. This is like a band reject filter, right? At the frequency 1 by root LC into 2 pi, you have a proper 0 at this circuit, at this output. So the transfer function will look something like this. So you are able to add by adding a series LC element between these two pins, between this pin and this pin, or this node and this node, between this node and the node here, I was able to achieve a band reject filter characteristics. If you want a band pass filter characteristic, I can simply add a DC voltage, an LC filter circuit. Okay, so these are all the different things that you can do. And for low frequencies, I am ensuring the gain is 0 because your L will short circuit. At high frequencies, the capacitor will also short circuit these two inputs, right? These are differential inputs. If the capacitor shorts them out, there is no differential component. So the transfer function will look like this. So mind you, these filter structures will give you filtering only for differential inputs. For common mode inputs, it will just act like an open. See, it doesn't matter. Let's say I'm connecting some impedance here, Z. If this node is at VCM, this node is at VCM, then both these will try to change this node by similar amounts. Any signal that is trying to change both these nodes by similar amounts this impedance will not draw any current for those inputs, for common mode inputs, which means it's not functional. You might as well remove it. So this offers filtering only for differential inputs. Okay, for common mode inputs, it doesn't offer any filtering. So you can add some impedance network here between these two pins and get the desired filtering you want for differential inputs. So it may turn out your input differential signal has some unwanted components. It has some supply noise over some frequencies or some additional noise you want to reject. Okay, then you can put some filter impedance between these two nodes and reject them. Common mode noise, by default the circuit is a differential circuit. The second stage is a differential to single ended converter. That will anyways reject all common mode noises of all frequencies. It will completely reject common mode noise of ideally, it will reject common mode noise for all frequencies. This filter that you are going to add will reject differential noise. Differentially, it will act like a filter for differential signals only. So that's the thing that to keep in mind. So that's where these two pins come into play. So pins FL minus and FL plus, or filtering pins. So that's it. I've covered everything that you need to know about instrumentation amplifiers. I covered it from a point of circuit designer as well. How would you spec your op amps if you want to design an instrumentation amplifier, from scratch, on your schematics, on your circuit schematics. Okay, on your IC, as an IC designer, if you want to build it from scratch, I've told you what are the things to look out for. And we also discussed very briefly at system level what are the things to look out for. Okay, if you're going to pick this chip, what are the things you have to look out for. Okay, so that's it about this. Thank you.